So you should have the basics of electric current and resistance and what an ammeter and a voltmeter is and things like that. Those were the videos you're supposed to watch on your own for the flipped classroom part. And then last week we talked about series circuits. Basically a series circuit is everything connected together in one loop. Okay. And then for a parallel circuit, now we're going to have something with several current paths. And then the total current's going to add up to the sum of what's in the branches. And so I'm going to show you some examples with the Castle kits, and then also on the notes we'll have an example problem together. So you get a little bit of a practice with this one. For the total voltage that's going to come from your battery, you're probably not asked to find that total voltage. It's usually given to you. However, as it comes out of your source or your battery, if you did have to calculate it, you could use Ohm's law and multiply your current and your resistance together. I don't think I left you a space, but if you wanted to kind of squeeze over in the margins, I'm going to show you a couple of schematics for parallel circuits. So the one that I did when I held it up, I happened to have 3 batteries. You can change your number of batteries. And then it would branch off like this. I did one light bulb, and then I created another light bulb. So if you kind of imagine looking at that, you've got one loop here and a separate loop for your second light bulb instead of everything being all together. So the current comes out and then it's going to split. Part of it goes here and part of it continues to the other section. I've also seen it drawn, and put my batteries back the same, where they'll branch off the parallel parts of your circuit like this and then group them back together. That's really just a personal preference on how you prefer to draw those. So in this case, it might be a little bit easier to see when you do this one that the current comes out of the battery and then it splits. Some current goes this way and some current goes this way. And then they're going to join back up together. And that original current that was through your battery, it joins back up and then it travels on through the rest of the circuit. So when you read the definition, the individual currents in each of the branches add up to the total that goes through the battery. That's what this is going to be. So it joins up together and you would add those together and then it goes back in. We are going to work our way up to doing a parallel circuits lab. So today we're just concentrating on the math, and then in your labs we're going to do a couple of series circuits labs where everything's all in one loop, and then we'll do a parallel, and then we're going to combine them together. So we'll have series and parallel all in the same circuit. So we'll work our way up to that before we take our next test. So remember, on a series circuit, the equivalent resistance, we just added all the resistors together and got a total. So this is one of the reasons we don't actually call it total resistance. We call it equivalent resistance because now we're not simply adding the values together, we're adding their inverses. And mathematically, when we get to our lab, you'll find out that as I add things in parallel, the total or the equivalent resistance is actually going to decrease instead of increase. So the opposite's going to occur with your series and parallel circuits. So we'll do a practice problem together, but I would add the inverse of each one. And then notice that when you total those together, that's equal to 1 divided by the equivalent. You will have to take the inverse at the end to get your final answer. And we'll practice with that a little bit later. And then remember that the sum of your currents is going to add up to the current that goes through the battery. So I'm just going to make you a little note over here. That through the battery is this one, and then our individual currents refer to the branches that we saw in our schematics, and then they're going to total up to what goes through the battery. So on our example problem, this time we've got 3 resistors, and they're connected in parallel with each other, and our battery is going to be 90 volts. Again, you could change that schematic if you prefer to do the split version. You could say resistor A, resistor B, and resistor C, and then they join back up together. It's a personal preference. Pick whichever way you want to draw your schematic. I don't know visually which one's easier for you. I'm just used to the boxy one, so that's the one I did first. And it does not matter which order you put your resistors in. Okay, so these could have been all mixed and matched around as long as you had one in each branch. And then I happen to label them A, B, and C in the order that they were given, just to kind of keep things a little bit more organized. Okay, so initially we were asked to find the current through each branch. Are they going to have the same amount or different amounts in the branches? Yeah, different amounts. So remember that the resistors split, okay? So each one has its own branch and each one has a different amount of current. However, they do have the same voltage or electric potential difference. So that's what's going to be different from series and parallel. Series circuit, it was the same current all the way through with a different voltage for each part. For parallel, it's the opposite. So now we're going to have different currents for each little branch, but they all have the same voltage for each one. So if I were to split this up and I wanted to find how much current was in the first branch, then I would take the voltage from my battery, which is 90, and just the resistance in branch A, which happens to be 60 in this case. And that's going to leave me with 1.5 amps going through that first little section of my circuit. And then you would just repeat the same thing for the other two branches. So for that middle one that we labeled branch B, remember the voltage or electric potential difference is the same for each of the branches. So that's going to be 90 volts. And then that resistor was only 30. So that leaves me a current of 3 amps. And you should start to see a pattern that as we lessen the resistance, the current is increasing. So those are inversely related to each other. So since we're keeping the voltage the same, my resistance and current are going to be opposites. And then you want to finish that out for the third branch. So again, the voltage or electric potential difference comes from the battery, so it's still 90 volts. And then resistor C only had 20 ohms to it, and that's going to give me 4.5 amps. So bigger resistance has smaller current, and then as we decreased our resistance, our current increased. You can kind of have a couple of notes. So for a series circuit, it was the same current everywhere in the circuit. But there was a different change in voltage or electric potential difference in the different parts. But there was a different change in voltage for the different parts of the circuit. And then for parallel, the voltage electric potential difference is the same for each branch. But now it's the current that's different. So those are going to be opposites to each other. So that's kind of a quick little summary. So part B wanted the equivalent resistance of the circuit. I'm just simply going to plug in to the formula. You don't have to do anything fancy. We're going to say 1 over 60 plus 1 over 30 plus 1 over 20, and that's going to equal 0.1. And on your calculator, I know some of you guys might jump to this and go, oh, that's really easy. I can find a common denominator. Not all your resistances will mathematically be that nice, but you could do that. So you could do a common denominator, or if you just want to jump straight to what you're going to plug into your calculator, you want to make sure that you open the parentheses and close them around each of those fractions for the inverse of all the resistances. And then you would equal. And this is where the decimal comes from. Remember that, oops, I added a 0, sorry. Remember that this decimal, however, is equal to 1 over the equivalent. So to get the equivalent resistance, I want to take the inverse of that decimal. So I'm going to do 1 over 0.1. And that should give me, sorry I moved it out of the way, I didn't realize it would box together. Should give you an answer of 10. I guess I could do it this way. So just don't forget that last step. Take the inverse. Okay, so for part C, it wants the current through the battery. Can you think of a way to find the current? Yeah. So we can add them all together. So that's one way. We found the individual current in each branch, so we could add all those together. And in this case, you're going to get 9 amps. Or, since we know that equivalent resistance of the circuit is the same equivalent that goes through the battery, I could also do Ohm's law. So you have that option, okay, and you end up with the same way, or the same answer. So if you're taking a free response question and it asks you something like this and you've got multiple ways to solve the problem, if you have the extra time, just go ahead and double check. And it's a way to kind of see if you're on the right track. But on the actual test, if you showed one or the other of those, you would get full credit just for showing one method. You don't have to do both. It's just a way to check your answer. And that's it for the parallel section.